All right, we started recording, so I think we can officially start our workshop. So hello, everyone. Welcome to our quantum computing and programming workshop, QNickel6. My name is Pavel. I'm one of the organizers of this workshop. I'm the CEO of the Quantum AI Foundation and coordinator of Q Poland, which is a local Q cousin of QWORD. QWORD is an international initiative and organization preparing those training materials that we'll use during this workshop. So before I give a voice to Stina, who will be our instructor, I would like to say just a few words about the organization. So as you know, the workshop will take place over 2 weekends, so 4 days in total. Justina will be the instructor. We also have several mentors, so if you have any questions, please you can contact them, and the preferable way is to ask the questions on our Discord server. But during the lecture, it is possible that Justina will also be able to answer your questions. So she will announce it. Yes, all the graphics were prepared by Agnieszka, who is also our team member from Q Poland. The training materials are available on the QWORDS website. They are called QNickel. And this is an intermediate level workshop. So it's not an introductory workshop. This is important. So we'll not explain the quantum computing from scratch. We already assume that the participants have some basic knowledge, at least, about quantum computing. The lectures will be over Zoom, and the communication with mentors and questions should go to the Discord server. You can receive a diploma, the certificate, after solving the Canvas homework. So Canvas is our platform for solving the quizzes, the final assignments. We'll send you invitations to Canvas, but probably later today or tomorrow, because there are still some things that we have to prepare first, and you must obtain at least 50% of the points from the homework, from each homework, and at least 70% of the overall points, so from all homeworks altogether. And the deadline to complete the last set of homeworks in Canvas is Saturday, or in fact, it's even Sunday, November 5th. So I will just fix it. But the deadlines are earlier for the first 2 homeworks. So there will be 4 homeworks in total. The first 2 homeworks will be announced tomorrow, and the deadline for them will be earlier. So it will be 29th of October. And next week we'll announce the next 2 homeworks, and the deadline will be November 5th. So that's the plan. Okay, so just to confirm what I've also said, this is an intermediate level workshop. So it's not introductory level workshop. I've observed that there were some questions on our Discord suggesting that some people may not be already on this, let's say, intermediate level. So we assume some basic knowledge at the level of QWORD's bronze workshop. So the bronze is the introductory level workshop for QWORD, and QNickel is one of the next intermediate level workshops. So it is a workshop for address to advanced quantum computing enthusiasts, professional researchers who have already completed the bronze workshop of QWORD or have similar knowledge at the level of the bronze workshop gained during some other lectures of workshops. So we can't promise that we'll answer some basic questions like what is a qubit, what is the Hadamard's gate, what is an entanglement. So we assume that the participants already know it. Okay, this is the knowledge that was provided during this introductory workshop bronze that we also organized a few weeks ago. All these training materials were prepared within QWORD. So QWORD is an international Organization. It's a network of individuals, groups, and communities collaborating on education and implementation of quantum technologies and research activities. So if you want to stay up to date with the events that are organized by QWORD, you're welcome to follow our website, fan page, Twitter, join the Discord. And these are some most important projects of QWORD. So Q-Bronze, Q-Silver, Q-Nickel workshops are 3 different workshops that we organize at QWORD. So as I said, Q-Bronze is the introductory level workshop. Q-Silver and Q-Nickel are more advanced, right? So these are like intermediate level workshops. And this is Q-Nickel. And we also organize some hackathons. We also have a research department. So there are some study groups that have meetings from time to time to discuss some newest research articles. There's also a Q-Intern program where senior researchers from all over the world can apply and propose their ideas for some internship projects. And then students from all over the world can also apply. And if they are selected by senior researchers, they can be guided, mentored during the summer and maybe also later. And they can work together on these research projects. We also work on let's say longer workshops, even something like academic courses or massive open online courses that last for even several months. So the ultimate goal, of course, is to prepare open educational materials for the universities that are interested in launching special programs or even studies in quantum computing. And as Q Poland, we are one of the Q cousins of QWOR, so there are currently about 30 Q cousins worldwide. So this workshop is organized by one of the Q cousins, that is Q Poland. So in fact, Q Poland was one of the 5 founding members of QWORD. And we have more than 10 active members, and we organize different initiatives like hackathons, contests, meetups, and so on. So you can also stay up to date and join our mailing list or our Facebook group, our Discord, follow our profiles in social media, subscribe to our newsletter to just stay up to date. All right, it's time for questions regarding the organization. So if there are any questions, it's now time to ask. And later I will just give a voice to our instructor, Justyna, and then we'll start the merit part of the workshop. So Justyna will explain it later. Let me check on our chat if there are some questions. So I just received some private messages that we are doing very well, and there are some questions about like introduction to quantum machine learning. So I can tell you that as far as I know, in QWORD, we are also working on such training materials related to quantum machine learning and also quantum annealing, QKD, quantum key distribution. So if you are interested, you can join QWORD, join our Q Education department. And in Q Education department, there is a special project that is called Q Kitchen. And there, the researchers from all over the world, researchers and teachers, enthusiasts from all over the world collaborate and work together on these educational materials that we can later use during our workshops. Okay. Yeah, I don't see more questions on our chat now. So I will now stop sharing the slides, and Justyna, if you are ready, the Zoom is yours and we can start the QNickel workshop.
Hello, everyone. Let me share my screen. Okay, I hope you can see the slide, QNickel Day 1.
I can see it.
Okay, thank you. So my name is Justyna Zawalska. I'm a PhD student in quantum computing at AGH University of Science and Technology in Krakow, Poland. And I'm also working as a software engineer at Academic Computer Center Cyfronet, also in Krakow. And today I will have the pleasure to conduct the first day of the QNickel workshop. This workshop should take around 4 hours today. We've started around 3 p.m. and we plan to finish around 7 p.m. So the anticipated agenda is as follows. So we have 4 days in total. And during the first day, which is today, we'll focus on quantum algorithms in Qiskit. Those will be, we will do, in fact, 4 Jupyter notebooks. And in these notebooks, there will be introduced the topics such as Qiskit introduction, classical gates, phase kickback, and Deutsch algorithm. Tomorrow, we will also be implementing algorithms in Qiskit, and it will be the Deutsch-Jose algorithm, Bernstein-Vazirani algorithm, and Simon's algorithm. And next weekend, starting on Saturday, we'll switch to solving MaxCat problem using Groover's search in Cirq. So it will not be in Qiskit, this second part. So first of all, we will start with the introduction to Cirq, and then we will have a recap of the Groover's algorithm. And on Sunday, which will actually be the last day of our workshop, we'll focus on the MaxCat problem and bipartite graphs, others and numbers checking, and Groover algorithm for the MaxCat problem. So let's start with the things we have planned for today. So the first topic is the introduction to Qiskit. It will be just a quick recap because as Pavel mentioned, we expect that the participants have some basic knowledge at the level of the Q Bronze workshop. So we are running the A00 Qiskit introduction Jupyter notebook now. So I will conduct this workshop in a way that I will show the content of the Jupyter notebook in here, run some cells and explain the most of the theoretical things that are in here. And then when there will be a part related to solving tasks, I will explain what is needed to complete this task. And then there will be a few minutes to actually complete this task by you. And when this time passes, we will come back to see the solution that I will implement. So if somebody will be able to implement this solution by themselves, it's perfect because it means that the knowledge was acquired. But if you have some troubles, don't worry, we will solve all the tasks together. So yeah, without further ado, I think we can start. If there aren't any questions regarding everything that I've said. Yeah, and I didn't mention what to do with the questions. So if you have a question related to what I'm explaining, or like anytime, please interrupt, preferably using your voice, because that will be the easiest way for me to see that there is, to hear actually that there is a question. But if you want to write a question on chat, that's also okay. I will check the chat every now and then. Okay, so I think we can start to implement something in Qiskit. We need to import this library first. So it's done simply with import Qiskit. Then we need to be able to create quantum and classical registers. Why do we need to do that? We need to be able to store, first of all, qubits. And second of all, we need to be able to store the measurement results, which are always classical values. So we need to be able to store classical values. So to store qubits, we use quantum registers. So we just need to create this an instance of the quantum register class, and we say how many qubits we want to have. So we in here we are creating a quantum register with 4 qubits. And the name of the quantum register doesn't really matter. It's just a variable. So it could be either a Q register or output. Yeah, both of them works. And so we know now how to prepare the qubits, like how to prepare the storage for qubits, but we also need to be able to have storage for classical bits, as I've said. So the storage for classical bits is created by instantiation of the classical register. So if, for example, we assume that we have 4 qubits, so it will be reasonable to also have a classical register with 4 classical bits, because if we want to measure the quantum register with 4 qubits, we will have like 4 classical bits of output. So as of now, we just have the storage for qubits and for classical bits, but we are actually operating on quantum circuits. So to create a quantum circuit, there are actually a few ways to do that. So the first and very convenient way is to first create a quantum register. So one, for example, then create the classical register, and to say that the quantum circuit will consist of this quantum register and classical register. So now I would like us to see how this quantum register looks like. We should be able to see something. Okay, so in here, it's just nothing. We have 4 qubits and a classical register storing 4 classical values. I will try something more, but I'm not sure it will help now. Okay, but yeah, so in fact, what we initialized with this circuit are 4 qubits. It starts with Q, so we have qubit 0, qubit 1, qubit 2, and qubit 3, and 4 classical values 0, C1, C2, and C3. There is also another way to create, it's the same way to create a quantum circuit, but we can have multiple quantum registers. So in fact, a few lines earlier, we've created a quantum register and output quantum register. So we can put both of them in here. We can create a circuit that doesn't have any quantum registers. I hope we will be able to see it. So yeah, in here we only have 4 qubits actually. But the last way to create a quantum circuit is to just use numbers. So the first number says how many qubits we want to have. The second is how many classical bits we want to have. And we can actually also draw that. So it's yeah, so we have 3 qubits and 3 classical bits. Okay, but just having this storage and the empty circuit doesn't help us, because we need to be able to manipulate this quantum circuit. So in here we will be using quantum gates. So when you want to use the NOT gate, you just do circuit.x. When you want to apply the Z gate, it's circuit.z, H gate. So Adamart gate is .h, C0 is Cx, and the first parameter in here is the control qubit, and the second parameter is the target qubit. The same applies for the CZ controlled Z gate. We have the swap gate and the CC0 gate. So we've created some quantum circuits. The operations are not that important now, but if we want to actually see what's in there, we can use the circuit.draw I've used it before, but we haven't seen the wires representing the qubits. And now when we applied some gates, we can actually see them. So let's take a look. So we applied X to the quantum register 2, it's correct. Then we applied Z to qubit 2, correct. H to qubit 3, C naught controlled by qubit 2 and target qubit 0, controlled Z, and we have control target here. Then we have the swap gate, so it's qubit 1 and 3, and then we have controlled control X. So we see this gate here. So the first option to draw a circuit is just to put the name of the circuit and then the function draw. But we can also have this circuit draw in a nicer way if we put this this option here, this parameter output MPL sending for matplotlib. We'll have a much nicer looking visualization. But yeah, it's basically the same. So now the task will be to create, the task for you will be to create a quantum circuit with 10 qubits, then apply H gate to qubit number 0, apply 9 CNOT gates where qubit 0 is the control and qubit I is the target, and we have the range from 1 to 9, both of these numbers are included, and then draw your circuit. And now I will say a word about how to return, actually not return, but let me know that you're working on these tasks. So I've created a text channel on the Discord. So the text channel is called Workshops, and you can actually vote using emoticons to log your activity during the workshop. It's like it's not important for you to get your certificates. It's just a feedback for me to know how many people are actually working on this task, how many people have finished, and if there are people who need more time. And based on these results, will be able to like have a nice pace that suits more of the most of the participants. So yeah, as of now, I think that 3 minutes should be enough for completing the task number 1 from notebook A00. And you are encouraged to find this Discord channel and vote with emoticons. Like what's your status? Yeah, so I will stop speaking now, and let's see in 3 minutes. Okay, time is up. So I see that the majority of people voted that they finished this task. So I will show the solution right now. So let me paste some comments to have everything clear. So first of all, so when we have a quantum, when we want to have a quantum circuit with 10 qubits, so we can start with a quantum register. Containing 10 qubits. And then so when we have this quantum register, we can create actually a circuit, which will be quantum circuit composed of this quantum register. Then we want to apply the Hadamard gate to the qubit number 0. So it's so we apply the H on quantum register qubit 0. Then we are applying 9 CNOTs. So for I in range from the range should be from 1 to 9. So from range from 1 to 10 because the upper bound is excluded. So it's circuit control X and the target. Okay, so control is 0. So it's quantum register of 0 and the target is QREG. No one, it's I because we are iterating in here. And then we want to just draw our circuit. So it's circuit.draw. And we want to have a nice looking out. So let's see if this works. Yeah. So what you should have seen in this task is the following circuit. This is the code. Are there any questions? Let me check the chat. Yeah, I can't see any questions regarding this first task, so I think we can move on. So we will learn a little bit more about gates. So it's a very interesting feature. So let's assume we have a quantum circuit with a quantum register containing a quantum register and classical register. And if we want to apply some gate, in this case, an Hadamard gate, we can apply it the whole register. So we don't need to, like, for example, iterate over the qubits. So we can apply this to the whole register, like doing only one line of code, which is very nice. So we have a quantum register of 10 qubits because this will be the register from the previous from the task 1 in my case, and we are just drawing it, so it's very convenient. And in here it's a very interesting feature. So sometimes you want to we want to create a gate that is actually controlled by more than 1 or 2 other gates, because, like, for example, we want to have a controlled NOT operation. So it's easy. You use the CX gate and controlled NOT. You might want to have the controlled NOT, the Toffoli gate, which is also already implemented. You just use CCX. But if you want to have a gate, it doesn't matter what's the gate, but this gate, when the gate needs to be controlled by more than 2 qubits, you actually, what you can do, you can import this gate class and write that you want to have it controlled by 3 other qubits. And you basically create your own version of this gate. This gate is controlled H gate. And basically all you need to do, you need to append it to our, so this is our circuit. We are appending this gate to the end of our circuit, and use in this second part, you say which qubits are the control qubits, and the last one will always be the target qubits. So 0, 1, and 3 are the control qubits, and 2 is the target qubit. And in here we were working on controlled gate, but you can also create like some special versions of gates. In here we have square root of x, and to do that we need to import the class for the x gate. Then there is a method called power, and we say that this should be square root. So exponent is 0.5. We just append this gate to our circuit, and we have a very interesting looking circuit now. So this brings us to the task number 2. And in here, you need to create a quantum circuit with 10 qubits, apply H gates to all qubits, apply X gate to the qubit 0, and this should be controlled by qubits 1 to 9, apply H gates to all qubits, and then draw your circuit. So as before, we will have 3 minutes for this task. And the timer will start now. Please log your activity on Discord. And we will hear each other in 2 minutes 55 seconds. From what I can see, people are still working, so we have 2 additional minutes now. Okay, now we can try to do this task together. So I'm pasting my comments here. So first of all, we want to create a quantum circuit with 10 qubits. So let's start with quantum register of 10 qubits, and then let's create a quantum circuit that contains this quantum register. Then we want to apply H gate to all qubits. So in here we can use this nice trick when we apply the H gate to the quantum register. Then we want to apply the X gate to, okay, no, this won't be that easy. We want to apply X gate to qubit 0 controlled by qubits 1 to 9. So we have the X gate imported in here already. So let's call this C9X because it's controlled. So C9X. So it will be X gate 8 class. And we say that it's controlled by qubits from 1 to 9. So it's 9 qubits controlled by 9. And we want to append this C9X to our circuit, but we need to say what are the control qubits and which qubit is the target qubits. So we know that, and the order is that first put the IDs of the control qubits. So it's it could be like range from 1 to 10 because we want to have 9 included, but we need to like wrap it in a list because we want to have it as a list. So we have a list of the control. So we just need to say what is the target, and the target is qubit 0. So we can just add an element to a list. Then we need to apply the H gate to all qubits. So one more time, we are adding it to the whole register, and we want to like draw this circuit. Let's hope it works. Yeah. So if your output looks similar to this one, then the solution is correct. Do you have any questions regarding task number 2? Okay, I'm checking the chat. I can't see anything in there. So let's go to the next things. Okay, it's running circuits. So in here, I would like to discuss something using a whiteboard. So I hope you can see my whiteboard, and I will try to write something. Yeah, it works. So I would like us to be all on the same page. So there are a few things I need to discuss because we will be writing a lot of quantum circuits today. So the first part is the initialization of a quantum circuit. So when we have some quantum wires, maybe this can be a little bit smaller. So those are quantum wires. So this is basically a quantum register. So this is Q0, Q1, Q2. So if we like don't know what are the value of, so basically what I want to say is that we are always starting the quantum circuit in a state 0, 0, 0. That's the state of all empty wires. And this state can be written as, so that will be 3 equivalent forms. So to write the state of this circuit, we'll actually use the bracket notation. So what we can write, it's either, sorry, we can write it as either get 0, there is no minus, but I can't erase that. That's weird. So please Let's take a look at that. So we can write it in the direct notation the following way. So it's 0, tensor product 0, tensor product 0. This is the same as writing that this is 0, 0, 0. So without using this tensor product signs, and we can also write it as 0, 0, 0 using only one ket. And this is equivalent to saying that this is the state when, so in the vector form, it will be 1 at the top, and it will be followed by 7 zeros. So we have 2 to the power of 3, which is 8. 8 rows in here. So that is what I wanted to say about the bracket notation, that sometimes we write this tensor product, but sometimes we won't. And now I would like to tell you a bit about how the gates on the circuit work. So this will be the third point. So we can have serially wired circuits. Serially wired circuits. So let's assume we have some state psi, and we apply some gate. It could be like a poly gate or basically anything. So we call these gates U1 and U2. So how we will write what's the state of these? So what's the final state of psi when we apply the gate U1 and then gate U2? So we will write it the following way. So it's state psi. Then we apply U1. So it's U1 applied to psi. And then we apply U2. So it's U2 applied to whatever was the outcome of U1, sorry. U1 psi. So at the end of the circuit, the result is U2, U1 psi. So that's important because the order is like from right to left when we actually write this as matrix multiplication. So basically what I wanted to mention in here was that it's matrix multiplication when we have a single wire looking like that, and we can have we can connect gates parallelly. So let's assume we have some state psi, and then we have some state phi. We have some gates. So it's a single qubit gate U1. We have a single qubit gate U2. So this can be written that it's U1 applied to psi and U2 applied to phi. But in total, the state is the tensor product between the top qubit, and the second, the bottom qubit. So it's U1 psi tensor product U2 phi. Yes, and it can be alternatively written as in the another form. So let's start the same way. So we have psi and phi. Then we write it as a 2-qubit gate, which is actually a tensor product between matrix U1 and matrix U2. So what we get here at the end, it's U1 tensor product U2 applied to phi. And so it's all when okay, cat phi tensor product cat psi. Sorry, but I forgot saying cat and just I'm saying that it's phi or psi. I always mean cat when I say that. So what we see from this is the property of the tensor product that we will be using very often in the course, and it's that when we have some matrix, tensor product, some matrix, and we are multiplying it by some vectors. So it works the way that we are multiplying the first matrix by the first state, and it's just matrix vector multiplication, matrix U1 times cat psi, and this will be the tensor product with matrix U2 cat phi. So this is the property that we'll be using very often, and it's and so this is an important thing, and there is also one other thing because it can be mistaken. So when we have two vectors, so it will be V1, no, it should be a cat. So when we have vectors, V1, cat V1, cat V2, and we have just multiplication in here, so it will be, okay, U, okay, U1 times U2. So in here we are multiplying everything by everything. So when we don't have matrices, but just vectors, we are multiplying it. So the result is V1, U1, cat V1, U2 plus cat V2, U1 plus cat V2, U2. So in this product here we have only like two things, and in here we have four. But yeah, we will talk about that when it will be needed, but I just wanted to mention it now to be able to easily see it. So that's it for now, and let's come back to running circuits. So I will in a second mention why I said that theoretical things a second ago. So in here we are creating a circuit consisting of a quantum register of 2 qubits, classical register with 2 qubits, and applying the H gate to qubit number 0. So let's display this. Let's display this this circuit. So because it's very important here, so let me find a function. Yeah, so I want us to be able to see the classical register, like whole classical register, not this truncated version. So I will also use the nicer interpretation, and after the Hadamard gate, I will also apply a barrier because I want I want us to be able to see a clear picture. So what do we see now in here? We have this Hadamard gate applied to qubit number 0, and that's the whole quantum circuit. And then we are measuring the results. And what we need to be aware of is the order of qubits in Qiskit. It's different than order in qubits, like for example in Cirq, we will see in 1 week, sorry. So the thing is that when we have the results, they are calculated. So when we have an output, the most important qubit is the qubit number 1, and so this is significant bit qubit, and this is like the second one. So the result in here, in the way like I will be showing it, is, so when we have some circuit and it's in the state 0 in here, I think it was a 0, yes. So we can calculate that by hand. So when we don't know like what, so if it's like just wire in here on the bottom qubit, we can write the identity gate in here because it doesn't change anything. So we are starting in state 0, 0, and then we are applying the H gate to qubit number 0 and identity to the qubit number 1. So we can write it formally like H tensor product I, and then it will be 0, 0. So this is H applied to 0, tensor product I applied to 0. So H applied to 0 is 1 over square root of 2, 0 plus 1. So we have a superposition now. And I applied to 0, okay, cat 0, sorry, I'm forgetting that, is 0. So now we can calculate the whole state. So the whole state is the superposition, equal superposition of 0, 0 plus 1, 0. Yes. So in my notation, so yeah, basically this is this is the easiest form. So in my notation in here, we always have 0 at the end because we are not changing anything. And on the top qubit, we have like 50% chance. That's so it's basically an equal superposition of 0 and 1, and after the measurement, it could either be state. So we are measuring in the computational basis, so it could be labeled as 0 or as 1. And this will be important because, so the way I write it is 0, 0, but the way you read it from Qiskit, you start with the bottom qubit. But yeah, so I would just explicitly mention when you need to think about that, but usually you don't. You need to be aware of that only when you are making measurements and when you want to interpret them correctly. So we will see that in here. Let me check that. So yes, so we want to execute this circuit. We are using a simulator. So this will be our backend. We are not using a quantum computer. So to simulate a circuit, to execute actually the circuit, you need to use this method to which you put as input a quantum circuit, the type of simulator, and how many times the measurement should be repeated. So in here, we can see that we got the result 0, 1, but 0 will be on the bottom qubit and 1 on the top, because we always expect to see 0 on the bottom qubit, actually. So the result, okay, maybe I should say it's 1, 0. Okay, so the result 1, 0, it's we get it almost half of the times, and the result 0, 0 is almost half of the times. So like it was just how many shots we got the 1 and in how many shots we got 0. And this is correct because the probability of obtaining both of the states is equal, but when we are just like making a random draw, the measurement results that don't really need to be equal all the time. So what's in here? Yeah, and this says that we don't need to measure all the qubits, we can measure like a sum of the qubits. So in quantum register, we have 2 qubits, but in a classical register, we have only 1. So it's like enough to create a classical register with 1 bit, even though we have 2 qubits. So we are basically running the same circuit in here. I will try to show it. So yeah, the circuit is the same, but we have only 1 measurement block in here instead of 2. So when we calculate the results, we only have 1 classical bit because the classical register consists 1 bit. So the task for you now is to implement this circuit. So you've already implemented the circuit in task number 1, and the thing you need to do now is to measure all the qubits and simulate this circuit 1000 times. So once again, it will be around 3 minutes, and please log your activity on Discord. We will wait 1 more minute. Okay, the majority of people have finished. So let's see the correct solution. So, oh, so it's not this task. So it's task number 3. So I've pasted the code from task number 1 we've done previously. So we just need to add the measurement. So it's circuit that measure, and we say it's, so we map the results from quantum register to a classical register. So in here, it's not a bug because we didn't need it earlier, but we need to have also a classical register with 10 qubits because we need to be able to store the classical results somewhere. So we need to add a classical register to the circuit. Maybe you've done it previously. So now we are supposed to use the local simulator. So the simulator, we are using this get Quasm simulator. Then we are creating a job to execute our circuit. So this job is execute. So we are implementing it. We are importing this from Qiskit. Execute the circuit with the following simulator, which is Quasm, and the number of shots should be 1,000, and we should calculate the results. So it will be counts. So take our job, get results, and get counts because we want to have them as the dictionary. So what we are measuring is the circuit we've defined earlier, and we just want to print the result, which is the counts. Yes, so we see, so let's take a look at how the circuit from task number 1 looked like. I think it was, sorry, I can't see it now. Should be this one. Yes, so if the first qubit is 0, then all of the rest should be also 0 because the CNOT will not fire. So we're starting in zeros in this qubits 1 to 9. But if the first qubit is 1, all of the other qubits also should be 1 because we will be inverting the bit from 0 to 1. So let's see. Yeah, we either have all zeros or all ones. Are there any questions to this task number 3? I see some questions regarding the assignments, so it's not for now. So there's one question about the thing I've said earlier. Why are the parallel gates a tensor product? I'm not really sure that I can explain the true reason why is that, but whenever we have wires that are parallel, and when we are in the Hilbert space, the gates are so the single qubit gates are matrices 2 by 2, and when we have 2 qubits, we want to, so the state consists of 2 to the power of 2, like the matrix, the vector actually is 2 to the power of 2, so the size is it's a vector of 4 rows. And when there will be 3 qubits is 2 to the power of 8. So I'm not really sure that I can answer this question correctly, but yeah, basically anytime you see parallel wires, you need to do the tensor product. Okay, I don't see any more questions now, so we will be finishing this A00 Qiskit introduction notebook soon, and there will be a break. So let's see the things that are last here. So debugging the circuit state representation. So we can see the state vector of the circuit. So in here, maybe I will print the circuit once again, but it's the same circuit we are using all over again. So we have a single Adamant gate on the top qubit, and we want to see what's the state vector. So we can print it as a matrix, and in this matrix form, we can see that the state vector should be 1 over square root of 2 ket 0, 0, and 1 over square root of 2 ket 0, 1. And it makes sense because it's the Qiskit order, it's reversed. So actually, this is 0 or 1, this first qubit, and this is always 0. That's the Qiskit order. But we can also see it in a nicer way. So we can see it using bracket notation. So in here we have 1 over square root of 2, 0, 0, and 1 over square root of 2, 0, 1. And we need to remember that this first qubit in here is actually the last qubit in here. And oh yeah, an important thing is that in here we have this version of a circuit, so we didn't have any measurements at the end, but actually we have one more line that's added there. Sorry, I need to rerun it. Yeah. If we add a measure, the state will collapse. So let's see. In here, we see that the output of the first qubit is 1, of the second is 0. It always be 0. But let's try again. Okay, we've tried again, and the state of the top qubit could be 0. So yeah, it's 0 again, but it's 1. So yeah, depending on what's the measured outcome of the Adamant gate, we will have either 0 or 1, and the probability of getting both of them is 50%. Let's see what's our time. I think that, yeah, so task number 4, we will skip this task for now. You can do it as like your homework. You just need to create a circuit with 4 qubits, apply the Adamant gate, and use the CZ gate, and measure what's the output and see which entries have the negative sign. So what might be like useful for you is to use this state.draw, because this will enable us to easier see which which entries actually have the negative sign. But we won't be doing this together. And the last thing is the unitary matrix representation. So you can get so when you like import the gate from the standard gates, you can have like some special version of gates. So you can define root x, so it's x gate to the power of 1 over 2. But actually what interests you is the matrix form so I assume that they are familiar with the CNOT gate. So it has the entries 1 on the main diagonal. Okay, sorry, I can't see that in here. Yeah, I see. So in the unitary matrix representation, the qubits are also swapped. So like I know that some of you, as well as I did a second ago, would expect to see 1 here, 1 here, 1 here, and 1 here. But actually, when the qubits are not ordered the way they are, like when we are looking at the top qubit and top qubit first, bottom qubit second, but the other way around, that's the correct version of how the matrix looks like. So you just need to be careful about this Qiskit notation. But if you want to see the unitary matrix, you can do that. And you can also use the unitary simulator. backend to do some calculations. So it's all what was in the Qiskit introduction. It was just a recap of what was introduced for sure in the QBronze, but I wanted us to be on the same page. So now I think we need a short break. So it's 4:19 Warsaw time. So I think that we can meet at 4:30. So it will be a 10-minute break. So if you have any questions, please ask them now, or we can see in 10 minutes. Okay, it's 4:30 now, so I hope we can come back to our notebooks. So let's change the notebook for notebook A01 classical gates. So now we will be talking about the irreversible and reversible computing, and to see the bigger picture, let's focus on the logical operations. So we know the operations as not, and, or, and maybe also XOR. All of them will be useful today. So for example, let's take a look at the truth table for the NOT gate. I hope you can still see my whiteboard. If not, just let me know, but I will assume you do. So for the maybe I will just make it smaller. For the not logical function, when we have input and output. So if the input is 0, the output is inverted, so it's 1, and if it's 1, it's 0. So in here, having when we have the output, it's actually very easy to tell what was the input, because if the output is 1, then the input was 0, and if the output is 0, then the input was 1. So we can actually see that, like, it's not a quantum gate what I'm trying to draw in here. So maybe I should like, okay, so it's not a quantum gate, it's not an X gate in here. I'm just trying to like draw that we have some input and some output, one input, one output, and we know that the result could be reversed based on the output. And when, for example, we have the not the AND gate, so let's write the truth table. It has 2 inputs and 1 output. I will create I will create another picture. So it's also not a quantum circuit, but I wanted to illustrate how the gate works. So yeah, so we have 4 possible inputs, and the output is 1 only if both of the inputs are in state 1. So it's 1 in here and 0 everywhere else. And the thing in here is that, okay, if we have the output 1, we know what was the input. So it was for sure 1, 1. But if we have the output 0, and even if we knew that one of the inputs is 0, we still don't know whether the first input was 1 and 0. So even if we have the knowledge of output and some knowledge of the input, because like if we knew the whole input, then why, like, we wouldn't be talking about like the need for reversibility if we know everything. So if we know that we have some knowledge, we still can't say what was on the other input. So that's why we say that AND is not reversible, because we can't, so we are losing some information. We know that the output is 0, but we can't really know what was the input. And the thing about operations in quantum computing is that we needed them to be reversible. So basically what we are trying to discuss now is that we can't implement the AND gate like in such a simple way. We need to have we need to use some, okay, it's not a trick, but we need to use something more to be able to turn irreversible computation into reversible computation. So I've said that AND is not reversible. And if we take a look at the OR gate, we can easily see that it's not reversible for the same reason. For example, if we have the output 1, and we know that one of the input is 1, we still don't know if the other input was either 1 or 0. So yeah, we can't just simply implement the OR gate. But if we stored the information about the input in the qubits, so if the input qubits could be actually not changed, we have a very nice way to calculate the output using an ancilla qubit. So we will show that. So it is shown in here. So when we want to create a binary logical function for two, for example, for two bit input, we will transfer it to qubits, but it's more or less the same. So we are not changing. We are not changing. Oh, sorry. We are not changing the values of the input qubits. So maybe I will try to annotate that. So let's focus on this right now. So we can call this first two qubits that they're like data qubits. Data qubits. And what's important is that we have ket x1 here, and at the output it's also ket x1. In here we have ket x2 and it's ket x2. So these two qubits, like their value don't change. And we have a third qubit that is not really like in classical computations, it's not needed. Okay, maybe we can see both of these things. But in here, it will be like target qubit that will store the result. And we will see in a second how it works. And target qubit. It works due to the fact that we have an XOR function, so it's addition modulo 2. So let's quickly see how the truth table looks for the XOR for the XOR gate. So let's write it in here. XOR, yeah. Okay. So we have two inputs. We have two inputs and one output. And when we have input 0, 0, and 0, 0, 0, 1, 1, 0, 1, 1, the result of the XOR operation is 1 only if one qubit is in state 0 and the other is in state 1. So it's 1 in these two cases, and it's 0 when both of the qubits are 0, and 0 if both of the qubits are 1. So what we can observe is in here, it's an interesting property here, that when we have 0, okay, when we have 0 XOR something, it's always this something. And yeah, that's basically what we would need more of the most often. The other way around, so if it's 1 XOR something, it's like not this something. But yeah, we will mostly focus on the fact that 0 XOR something is this something. So if we choose wisely and we set this ancilla target qubit to some value that we need, we can need it to be in state 0, for example, and we have 0 XOR value of the function, it could be like, a function that returns a binary output, we can store the result in this Ancilla qubit. And in this way, we made this computation reversible because we still know what the input values were. So even though the AND operation is not reversible, we can implement it in a reversible way using this approach. So we will store the data qubits unchanged, and the result of the AND operation will be stored in this target Ancilla qubit. So let's actually see the task number 2. We will do it together. So we have a truth table. So we should complete the following table, and we have the input values and the third register for the output. So let's leave it in here. Maybe just enough. Yes, okay. So let's fill in this table. So x1 and x2 remain unchanged everywhere. So I can write this down. And now we are computing the XOR. So it's 0 XOR, and it's x1 and x2. So 0 and 0 is 0 and 0 is 0, and and 0 XOR 0 is 0. So in here, the value will be 0. In the second row, we have y, which is 0 XOR x1 and x2. So it's 0 and 1, which is 0, 0 XOR 0 is 0. In the third row, we have 0 XOR 1 and 0. 1 and 0 is 0. 0 XOR 0 is 0. And in the last row, we have 0 XOR 1 and 1. 1 and 1 is 1. 0 XOR 1 is 1. So in fact, if we just calculated x1 and x2 in the next column, we would get 0, 0, 0, 1, which can be also seen in here. Oh no, sorry, you can't see that actually. Yeah, you can see it now. So yeah. And we see that the output of the third qubit, so this qubit in here, calculated the value for the AND function. So we wrote an irreversible gate in a reversible, an irreversible operator in a reversible way, and it's due to the fact that we used 0 in the target qubit register, because 0 XOR something, it's always this something. So that's the trick we used in here. Are there any questions regarding that? Okay, I can't see any, and I can't see any on the chat. So before we come to the task number 3, which you will be implementing, I would like to focus for a second on task 3 prim, which is design a quantum reversible circuit for implementing XOR gate using an Ancilla qubit. So it means that store the original values of qubits. So the thing is, we will do it together now. So we are trying to implement XOR, and it might sound silly because we know an efficient way to implement an XOR. So let me write it. Okay, so usually when you want to have an XOR, you just have, so it's 2 wires, you apply the CNOT, and in the top qubit you have A, and in the bottom qubit you have A XOR B, and it's a perfect way to implement the XOR function. But sometimes it might be useful to have another qubit so the output of the bottom qubit won't be actually the value of the function, but just it will just be the value of b, and we will have another qubit in which we will store the results. So we can think about how to implement a function like that. So we can have a and b, and so we want to use this ancilla qubit, target qubit. So let's start in the state. Let's start in the state 0. Okay, we are talking in here either about states or binary values. So yeah, we can talk about states. So I'm adding cats everywhere. Yes. And in here, when we have A and B, and we want this to behave like XOR, what we can do is we can check if the value of the first qubit is 1, then change the value of this bottom qubit to 1, because the XOR will be only satisfied if it's either 0 or so it's 0 on one of the qubits and 1 on the other qubit. So this will work for the following case. So when we have 0 in here, there are 4 cases we need to take into consideration, but we'll do it in a second when I finish the circuit. And actually, we just need to apply one more gate. And I will explain why it works in a second. So the thing is that we have this circuit. Let me copy it. Okay, and we will think about all the possible values. So the bottom qubit is never changed. So it's always 0. So let's assume we start in state 0, 0. So it's 0 in here. So this CNOT will not fire. So the state is still 0. Oh, sorry. Still 0 after this CNOT gate. So this 0 will not fire this CNOT. So it still be 0. So the output is 0, and the input remains unchanged because we didn't apply any other gates. So let's try something else. Let's try 1, 0. So the input remains unchanged. So it's 1. So this first CNOT will fire. So this 0 state in the bottom qubit will be switched, like inverted. So sorry. So we'll have 1 here, but it's 0 on the second qubit. So this next CNOT will not fire. So it still will be 1. So we have the result 1 stored in here, and it's correct because it's 1, 0. We can have the alternative option, which is 0, 1. So this first CNOT will not fire, but the second will, and the output will be 1, which is correct. And the most important thing, it should not give the result 1 for the 1, 1 case. So let's assume we have 1 in here and 1 in here. So the output is the same. So if we have 1 in here, then this 0 is changed to 1. We have 1 on the second qubit. So this 1 is actually changed to 0 because it's not and not. So it's 0. And at the end, we get 0, which is the proper value of XOR for the input 1, 1. Are there some questions? I see. I see a question. So the question regards which qubit to measure in the last circuit to get the final output Y. So it will depend, but in the simplest case, you will want to measure the last qubit value. So that's the output of the function. But in a second, so in the next in the next notebook, we will see that actually sometimes the result is somewhere, it is not in the place we would expect it to be. So we know the trick now. So to use an ancilla qubit, we know the how to implement reversible XOR gate, and maybe I will. So it's basically two CNOTs. And now the task for you is to design a quantum reversible circuit for implementing OR gate and test the circuit on all possible 2-bit inputs. Measure only the output qubit. So what I would recommend to do now is that first of all, you need to be careful because this input is in Qiskit order. So this is like the bottom qubit and this is top qubit. If somebody does not want to cope with that, I will paste some code with a hint a few seconds from now, but maybe somebody wants to implement it by themselves, so I won't spoil all the fun. So we will have around 5 minutes with the possible of extension. And yes, you can start to try to work on this task number 3. Please record your progress on Discord. I can see that people are still working, so we will have another 3 minutes. Okay, I think it's time we can come back to doing it together. So let's see what we have in here. So in task number 3, we need to implement reversible OR. And the fact that I've shown you how to implement XOR in a different way has some meaning. There is more than one way to do this task, but I will show the simplest one, I think, from my perspective. So we know how this circuit looks like for the XOR function. So that's the circuit you can see in here. And when we actually take a look at what's the difference between XOR and OR, it's the difference is in the last part. So if the both inputs are ones, then the output should be 0. And if in the case of XOR, and if the both inputs are 1 in the case of OR, it should be 1. So what we can do is just apply a minor change to this circuit, which is actually just adding another gate. It's the Toffoli gate, so it's we have 2 control qubits. And why should it work? So let's take a look at all the possible input-output values. So let's assume we have 0 in the bottom qubit to calculate everything easily. So let's start with the 0, 0. So this first CNOT doesn't fire, the second also, the third also not. Inputs don't change, and the target qubit also remains 0 because the CNOTs didn't change anything. So then we have the case 0, 1. So it's 0, 1. Input remains the same, and let's see if anything changed. So this first CNOT doesn't fire, this second does. So we can have, so we have like 1 in here. So we will change the third target qubit to state 1, but the third, so the Toffoli gate won't fire because the first qubit is 0. Here we have 1, but we need to have both ones. So we will have 1 as the output, which is correct. And then we can try the version with 1, 0. Okay, I'm not able to erase this 0. So let's try 1, 0. So the input remains unchanged, but we have 1 here. So this first CNOT will fire. We will have 1 here. The second CNOT won't fire because we have 0. So this state remains unchanged. This third, so this Toffoli gate won't fire because we have only 1, 1, but we need 2. So it doesn't change the bottom state, which will remains 1. So OR of 1 or 0 is 1, which is correct. And we need to check the last most important case, because that's the difference between OR and XOR. So if we have 1 and 0, the first CNOT will fire. So it will be 1. So this will change our state from on the bottom qubit from 0 to 1. The second qubit will also fire, so it will actually change the state to 0. So that's the XOR version, but we need it to have be 0. So if both of the qubits are 1, then actually invert the last qubit the next time. So we don't change the input and the output is 1. So actually writing a reversible OR is basically adding a controlled X, because what's the result when the result for OR is 1, when either the first one is 1, the second one is 1, or both are 1s. And in the case of XOR, both cannot be 1 because then it will be 0. So let's quickly implement it. I've shown you a hint about how to cope with Qiskit order. So that's the value of the bottom qubit. So if the input of 0 is 1, then apply X gate on the bottom qubit. If the input of 1 is 1, then apply X on the top qubit, because we need to just initialize the circuit. So basically we just need to put different values, 0 and 1 in this place. And we know that this quantum circuit contains 3 qubits. So the first thing we need to do is apply the controlled X from 0 to, from 0 to 2, or it was from 0 to 2. Then another CX, it will be from 1 to 2. So 1 is control, 2 is target. And then we have this controlled X. Controls are 0, 1, and the target is 2. Then we need to just measure the circuit. Like just add measurement gates. It's not gates, measurements. Measure to 0, and let's see if it works. Yes, so 0 or 0 is 0, and we got this output 1,000 times. We measured it 1,000 times, so that's what we expect. Then we 0 or 1, 1, 1 or 0, 1, 1 or 1, 1. And that's all for this task. Yeah, do you have any questions regarding that? Okay, I don't see any on the chat, and I can't hear any. So we will skip the task number 4. You can implement it yourself. So this is the description of the task. But there is one important thing. There is a change in the Qiskit code. So if you downloaded the notebook from the GitLab, you have an older version of Qiskit in this notebook. So you would need to apply 3 changes actually, because the operator U, which is this, defined in here, doesn't have this len this method len won't work on it. So we need to use u.dim of 0 in the first 4. In the second 4, we are taking the second dimension, and actually it's not like an ordinary array. We just need to access it as data ij, but you don't need to worry about like writing it now. It is so this change is published on the Google Drive folder. So in the same folder in which you had the instructions how to install the Qiskit, and there was this README file. So I can later also post this on some other channels. So this is not important from now, but we have 2 remaining tasks in here. So the fact is that we can implement any Boolean function. So this first X register can have like multiple qubits, like n qubits, and in this output register we can have multiple. We can have the result of computing this f of x, which the x input has multiple inputs. And to do that, we just are defining a quantum operator. So this operator works in a way that we take a first quantum register, the second quantum register, and the effect is that the first register remains unchanged, and the second has this XOR operation. So now there will be 2 tasks for you. I hope I've wrote them on our Discord. Yeah, task 5 and 6. So in the first, so it's pen and paper task. In the task number 5, you need to prove that UF is reversible. And in task number 6, you need to apply the operator UF to this 2 states. But please do it only for this first 2 cases. So cat y equal to cat 0 and cat y equal to cat 1. We will work on the minus state in the next notebook. So now you will have around 8 minutes to complete all these tasks, and I will come back to you. You will have 2 additional minutes. Okay, we can solve this task together now. So let's see once more. So we need to prove that this operator UF is reversible, and what we are given is the value of x and the output y XOR f of x, and we need to just compute the y. So we know what is given, we know what we want to compute, so we can use. So what we can write is, so this is the first thing given, and we can actually XOR it once more. If the f of x, then we are using the associativity of the XOR function. So we can write that is y XOR f of x XOR f of x. If we XOR the same things, they have the same value. So this XOR will be 0. So we're using an XOR property, which means that what we basically have is y XOR 0. So it's 0 XOR something. So it's this something. So which is this y we were looking. So given these things, we computed y, and that's what was required in task number 5. Is there something on chat? I'm not sure. So there is a question on chat. I'm not sure regarding which task is this question about. We need to execute a simulator or just start a state vector representation. So if you please could clarify that, I will answer. So the question is what actually, for which task is this question? So now I will move to the task number 6. I will focus for now only on this first two the things that need to be calculated. So maybe let's write it in here. So it will be task 6, and the circuit looks as follows. We have UF, the input is unchanged, the target is y XOR f of x. So in the first case, we have that cat y is say 0, so y is equal to 0. So we don't really care about what x is, so maybe I will copy the circuit. Give me a second. Okay, we will need it 2 times. This will be faster. Okay, I will come back to the explanation right away. So if y is 0, okay, is it 0? No. Sometimes I can't write in here. Okay, I hope you can see that it's 0 here. We have on the target register, we have 0 XOR this function. So this is basically the value of the function. But in the second case, where cat y was equal to cat 1, we have 1 in here. So it will be actually negated value of this function. Do you have any questions regarding these two subtasks? So in neither task 5 nor task 6, you don't need to write code for that. So you can and execute it in simulator, like whichever version, either the classical option or like the standard option or the state vector simulator. So for now, I think it's time for another 10-minute break. And after the break, we will be doing the next notebook. So let's meet at 5:45. I hope we are all back together now. So we've finished the notebook A01 classical gates, and now we'll focus on the notebook A02 with phase kickback. So we'll talk about eigenvectors and eigenvalues. So the eigenvectors and eigenvalues of unitary matrices are special. So assume this U in here is a unitary matrix, and we have some state ket psi. And if so, for this unitary matrix, we can find its eigenvalue. That for this same state, it is ket psi, and we'll in here call it its eigenvector. So in here, if we, hey, somebody's writing on the screen. Oh, thank you. So if we apply U to some particular state, we get exactly that particular state, because the state in here doesn't, oh, sorry. This was supposed to be a highlighter. So the state remains the same, but it has some coefficient in front of it. So this lambda coefficient. So what this is effectively doing is adding a global phase onto that particular eigenvector, this state. So in the notebook, they ask us to see how the so that they ask us to see that what happens if we start in the state minus and then apply the NOT gate. So let's actually calculate that. So we have minus state, which is equal to 1 over square root of 2, 0, 0, minus 1. And then we are applying the NOT gate. So what we have now, we are inverting 0 to 1 and 1 to 0. So it's 1 over square root of 2, 1 minus 0. So basically, we can take the minus before, so like pull out the minus in front of the parentheses. So it's minus 1 over square root of 2, 0, minus 1. So it's the same thing as before, but we have minus somewhere else. And we can see that this 1 over square root of 2, ket 0 minus ket 1 is the minus side. So what we have is the minus state. So we started in ket minus state, and after applying the X gate, so not in here, we got minus before of that. So it means that when we, so I can write it in a different way. So when we have X gate applied to the minus state, it's the same as having minus 1 multiplied by this minus state. So minus 1 is the eigenvalue of the poly X gate. And in the task number 1, they ask us what is the other eigenstate of the NOT operator and what's the corresponding eigenvalue. So we'll do that together. So okay, so to calculate the eigenvalues of the matrix poly X. So the matrix representation of poly X is 0, 1, 1, 0. We need to solve the characteristic equation. So the characteristic equation is that the determinant of this x minus lambda times identity should be equal to 0. So let's calculate that. So it's 1, 0, 0, 1 minus lambda 1, 0. Oh no, it's the other way around. 0, 1. 1, 0, yes, now it's correct, I think. So it's the same as that of, so it's 0 minus lambda, 1 minus 0, 1 minus 0, and minus lambda. So to calculate the determinant of that, we just need to, so first of all, we'll multiply the elements on the, so it's a 2 by 2 matrix, so we multiply the elements on the main diagonal and then subtract this multiplication of 1, 1. So it's minus lambda times minus lambda minus times 1 times 1. So it's lambda squared minus 1, which is, you can use. So this can be expressed in this way. So actually this whole thing is equal to 0 when, so this has two solutions. The first one is 1 and the second one is minus 1. So this minus 1 is actually a good thing that we got it in here because we saw this eigenvalue here, but we got the other eigenvalue, which is plus 1. So we would like to see for what kind of state we have this eigenvalue 1. So what we can try to do is, so now let's write that we have poly x acting on some vector with components x1 and x2, and it's the same as like this, applying lambda 1 to the same vector. So we can actually apply this x gate to this vector x1, x2. So we will just switch places of x1 and x2. Lambda 1 is equal to 1. So we will see that it's just x1, x2. So from here we see that it's that we have x2 x equal to x1. So that's the so that's what we can put into this vector to have this eigenvalue 1. But also we know that to have like a correct quantum state, the amplitudes should add up to 1. So x1 squared plus x2 squared should be equal to 1. Yeah, because that's just basically normalization. So from this, we know that such a state should be 1, 1. That's a simple state because x1 is equal to x2, but the normalization factor would be 1 over square root of 2. And this is the vector notation for the state plus. So now we can check whether we did it correctly. We won't calculate the second eigenvector because we already know that it's the minus state, but just quickly verify what happens if we apply x to the plus state. So it's actually x applied to 1 over square root of 2. I hope you can see it now. 1 over square root of 2 at 0 plus at 1. So it's still 1 over square root of 2. Okay, 0 inverts to 1 and 1 inverts to 0, but it didn't change anything. So it's still the plus state it's 1 times this plus state. So it's the correct eigenvalue for this vector. So we know that the other eigenstate or eigenvector, that's the same thing for the not operator. It's a plus and its eigenvalue is 1. So we have minus with the eigenvalue minus 1 and plus with the eigenvalue plus 1. Do you have any questions regarding that? Okay, somebody wrote a very nice comment that we could say, that x squared is 1, then its eigenvalues are plus 1 and minus 1. Thank you. So what's actually phase kickback, by the way? Okay, so this is, we will see that in a second in here, but basically, okay, so yeah, maybe I will try to do a very short digression in here. So we have some unitary matrix, sorry. We have some vector. And in the general case, we will have, so when we do that, we will introduce the phase factor and we will write it as e to the power of I some angle and this same state. And if we try to write this in a circuit form, we will have, for example, in here, 2 qubits. And it's important that the bottom qubit is this eigenvector. So we have the same psi in here and on the bottom qubit. And then when we, for example, apply the Hadamard gate and some control to U operation in here, this, due to the fact that, so we know that this gamma, when they have applied this operator, so no, sorry, it's not gamma, it's psi. This psi, when the applied operator is U, it's the same as applying the phase. So it's a fancy way to say that we want to apply some phase gate to the top qubit. So actually, if you take a look of, okay, in here we have the Hadamard gate on the top qubit. So the top qubit is changed, but it's not changed in the way we would expect, because we would expect the matrix to be in here like 1 square root of over 2 1 1 1 minus 1, but it's not. It's so instead of applying a phase gate, we have something more complicated. And the question is, why do we need to have something more complicated if like there exists phase gates? So the thing is that sometimes in the process of computations, we can translate some function evaluations into these phase factors. So we will see that in a second how does this work in the Deutsch algorithm. So we are applying some gates to both of the qubits, but the result is stored not on the bottom qubit but on the top qubit. It will be clearer in a second, I hope. And yes, e to the power I theta, this is the same as lambda in the case of unitary matrices. I just used a different notation. So let's see what is written in here. Maybe I will also show it on using pen and paper. Maybe it will be a little bit. Okay, let's leave it for now. A little bit more clear. So we have 0 and minus. And we apply a CNOT gate. That's what they said that we need to do. 0 and minus, apply CNOT and see the effect. So the effect in here is like there is no effect. because CNOT doesn't activate with 0, so it stays the same. But if we had, in the other case, they ask us to calculate in here, it's 1 and minus. So let's see it in here. The top qubit remains unchanged, and we need to see what's the effect of the CNOT gate. So let me write that. So the state is 1 minus, and then we apply the CNOT. The first one is the control, and the second one is the target. So maybe before I do that, I will say what this state really is. So this state is 1 tensor product 1 over square root of 2. Okay, I can't see that. So I will write it again. One over square root of 2, it's a minus, so it will be cut 0 minus cut 1. So in fact, the whole state is 1 over square root of 2. 1, 0, minus 1, 1. And then we want to, so yeah, that's the state we have, 1, 0, 1. Then we want to apply the CNOT gate. So what we will have, the first is the control qubit. So it 1, 0 will turn, so this is control, so this should change. It will be 1, 1 minus, this is control, so this is target, so this will change to 1, 0. We can take 1 before, so take it in front of the parenthesis, sorry. 1 minus 0, so it's 1, 1 minus 1, 0. And if we take a closer look, we can write that it's still 1 times 1 over square root of 2. 1 minus 0. If we take the minus, so if we pull it out in front of the parenthesis, we will get 1 tensor product minus 1 over square root of 2, 0 minus 1, which actually, so this without this minus, so we need to remember about this minus, is the minus state. So we have minus 1 and the minus state on the bottom qubit. So so what we actually can see when you, sorry. So what we actually can see, oh, sorry, you are not able to observe what I was writing, my bad. So when we have this, this circuit, on the top qubit, we have minus 1, and on the bottom qubit, we have the minus state. So it's very interesting because we didn't do anything to the top qubit. If we like just take a look at that, because like we basically applied the CNOT, but due to the fact that that we have this minus state in here, and the way it behaves with the CNOT when there is 1 on the top qubit, we will have this global phase kicked back to the top qubit instead of like being anywhere else. Let me see the chat. So does the phase gate applied in the, so the question is, how does it affect other states, I think, because so so let me read the questions. So does the phase gate applied in the first gate affect the second qubit? I'm not sure what you mean by the phase gate, because we don't have phase gates in here, or maybe this was referring to this thing. So if yes, the phase gate affects the first qubit. Yeah, so both of the qubits are affected, and essentially when you have a CNOT, you cannot think about these qubits like being separate things. After they are entangled, they work together. So how does this affect other states? The answer is that if we have some eigenvector in here that will have some eigenvalues that will cooperate with it, because for the CNOT, the eigenvalue, only the phase or sign that changes. So yeah, what we will have will be the phase changing on the first qubit. So a phase can be can be seen as the sign, because the absolute value of this should be 1, I hope. So yeah, I hope this answers your question. So this phase does this affect our does it? No, it does not. Sorry, let me think for a second. It depends. So in here, the sign would not change anything because it's like a global phase, but in we will see how it works for the Deutsch problem, in which yeah, we can we know the measurement results based on what was there. So it can lead to errors at end. So there might be some issue with my explanation, because no, it should not introduce any errors. It's just a quantum trick that puts the phase somewhere else, and then they enables us to get the result on like some other qubit. So I think that maybe if we take a look at some other examples, we will be able to like see it more clearly.
Can I ask a question like that?
Yeah, sure.
Okay, so from what I recall, only relative phase has a physical effect. So from what I understand, this phase changing in the first qubit is a bit of an illusion, because like we can kind of choose a global phase arbitrarily.
So you are totally right. The relative phases between two qubits can be measured, so that's true. And if there is a global phase, we can measure that, but it can. So even though we can't measure it, because we don't always need to measure everything, we can use it for some computations, and this phase can affect some other gates, and in the end, it might be helpful.
Mm-hmm. Okay, but here we are changing the relative, like here we have a change in relative phase between these qubits, between these states. So this has a physical effect. I understand that, but like from what I understand, it doesn't really matter if the first state is has a minus sign or the second state has a minus sign, from the like computational perspective. Right?
I'm not
Am I
super
right?
sure about the answer to this question, but if we take a look at the mathematical formula, there are like two cats, we need to have minus somewhere.
Yeah, so like it essentially doesn't matter if we write it with a minus in front of the one cat or a minus in front of the minus cat.
I think so.
Okay, thank you.
I might be mistaken, so I need to check that. Okay. I will
Okay,
make
sure.
a comment about that. Okay, so what's the time? We have 1 hour left. So I think we need to, if this is more or less understandable, we need to so maybe we can also do this this next circuit to see why it really changes something. So let me rewrite this. I will check and change to my whiteboard in a second. So we have, so I'm talking about this circuit. It's some superposition of A0 and beta1. Now I'm thinking about whether the thing I've said earlier was correct. So I'm not sure. Please give me some time to answer your question about where the minus should be. Because in here you see that the minus is on the top, and I will say why in a second. So we are starting in a state that is alpha 0 plus beta 1. So some superposition. Then we, and on the bottom qubit there is minus. So it's not a coincidence that there is a minus in here. Then we have the CNOT, and there is alpha 0 minus beta 1 as the effect. So let's see why is that. So let's try to calculate it. So at the beginning, we have state alpha 0 plus beta 1. This is tensor product with minus, and this equals to, so the first, it's 0 minus plus beta 1 minus. We are applying the CNOT. So the first qubit is the control, the second is target. After that, so in the first case, we have, no, it's not equal. It's 0 as control, so the minus state doesn't change, but in the second case, it's 1 in here, so we should change this minus state. And from the calculation a few lines above, we know that if we have the state 1 minus, so this is the state 1 minus, beta is just the coefficient, so it doesn't matter. So 1 minus is like translated to this minus 1 minus state. So we will just change the sign here, and the minus state will remain as it was. And this is basically equal to alpha 0 minus beta 1 tensor product state minus. So we see that this minus state is at the bottom. So this didn't change, but the phase got kicked back to the upper qubit. So can we have this minus on the bottom qubit? I'm not sure, because the way that we put it to I think that's the thing we want to do, to put it like to the other qubit, not the qubit we are right now at. And when we do it this way, and when we always like put it to the top qubit, it doesn't need to be top qubit, but the other qubit, not the one when we have this target. It's alpha 0 minus beta 1. I don't know. Do you have any questions about that? I can't hear any. So and now I think it's time for task number 2. You will be able to implement something. So I think maybe 5 minutes for that, and maybe we will extend some time. So it's notebook A02 task 2. Okay, so I think we can do this task together. So I'm pasting some comments. So first of all, we need to create a quantum register with 2 qubits. So it could be quantum register with 2 qubits. Then we need to create a classical register also with 2 qubits because we need to measure the results. Then we create the quantum circuit consisting of quantum register and a classical register. We need to set state of quantum register 0 to 1 and quantum register 1 to 0. So if something needs to be 0, we don't need to do anything. So quantum register 1 is already in the 0 state. We need to set quantum register 1 of 0 to state 1. So we are just applying the X gate. And quantum register 1, it will be helpful for us to have a barrier that will, it's not important. I will have a barrier to better show you the circuit. Then we are applying Hadamard gate to the to both of the qubits, so we can okay, we are applying to quantum register 1, then we are applying the CNOT operator, which is the X quantum register. Control qubit is Q1 actually, and target is Q0. Then we are applying, we are applying Hadamard gate to both of the qubits, so the whole register, and we are doing the measurements. So we are mapping quantum register 1 to classical register 1. Okay, yes, it's my circuit 1 everywhere. Sorry for this typo, but we will see the correct result in a second. So, but maybe before we see that, let's print how actually this circuit looks like. So we see, okay, I have too many x's. There should be x only on the top qubit. So I have this code prepared earlier. So I think I had some typo earlier, but it's not that important. Let me write, let me display. Yes, it works now. So we have only x on the top qubit, and I want to have a barrier on the quantum register because I want this x to be separated from this Hadamard transfer CNOT and Hadamard. And when we execute this, this thing says that we are starting in the state 1, 0, and the state 1, 1 is observed 100 times, and we were measuring it 100 times. So we are certain that the state is 1, 1. So actually, we can analyze why is that. So I will rewrite this circuit. So we can see the circuit in here, and we will try to calculate by hand why it works the way it does. So we are starting in the state 0, 0. Then we apply the X and I gates, and it's after that it's 1, 0. Then we applied Hadamard gates. So Hadamard applied to 1 tensor product Hadamard applied to 0, which is actually 1 over square root of 2, 0 minus 1, tensor product 1 over square root of 2, 0 plus 1, and when we calculate that, it's 1 over 2, 0, 0 plus 0, 1 minus 1, 0 minus 1, 1. And that is all we need from now. So we have calculated up to here what's the state. Then we have the C0, and actually the first one is the target and the other one is the control. So it's 1 over 2. So this is control, so we don't change anything. This is control, so we change it to 1, 1. This is control, so we don't change anything. This is control, so we change it to 1, 0. No, something is not correct. It should be. Sorry, because the state is not correct. I will find the mistake in a second. So, no, do it. Let's do it once.
I think in the last cat, it should have been 0, 1. And I see Ragunav on chat thinks so as well.
Okay, so sorry, okay, maybe I shouldn't do that. So once again, I will do it quickly because I don't know how. Okay, maybe I can revert it. Oh yes, I can. Cool. And yes, so the comment was where is the mistake? Sorry, 0, 1 at the end. Okay, yes, you are right. Thank you very much. Yeah, it works because we're like inverting this one. Yeah. Cool. So what we have now is actually we can like split it into two parentheses, and the first one should be 0 minus 1, and the second also 0 minus. Does it work? It's 0, 0, minus 1, 0, minus 0, 1, minus 1, 0, plus 1, 1. So yeah, if we multiply that, and there is, of course, tensor product in here, it works. So basically, if we don't write it this way, but if we put 1 square root over 2 in here, we can see that the first thing is the minus state, and the next thing is the minus state. So we have calculated everything up to this point. So we've calculated what's after the CNOT gate. So now we are applying 2 Hadamard gates. So it's HH, and when we apply Hadamard gates, sorry, it does not work well. When we apply the Hadamard gates to the state -1 minus, we get the state 1, 1. So, and the thing we have from our code is that when we have the state 1, 0 as input, 1, 1 is observed 100 times, and that's true. We see why, because it always is 1, 1, and I see a very nice comment that 1, 1 is the output, and somebody counted it before I did, so very well. And I just wanted to show one thing that you can prove later when we finish our call today. So when you have a CNOT gate between, I think I've seen this terminology somewhere, a Hadamard sandwich. So we have a Hadamard transfer something and another Hadamard transfer. It's basically like applying the C0 the other way around. And it would make sense because if we see that this could be basically an X and C0 implemented this way, we can easily see that if we start in 0, then it's 1 and this will always fire. So it's 1, 1. So that's all for this analysis that's in here. So you can also read about that. But sometimes the explanations are in Qiskit order and sometimes they are not. This explanation is in Qiskit order. So they start in state 0, 1. And the explanation is like the bottom qubit first and target qubit first. But the other explanations are in the other order. So looking at the time, we will skip the task number 3. But you can do it afterwards because it's you just need to implement the circuit with 7 qubits, do the operations, and see on which which qubits do you see the phase kickback effect. But what's most important for us now is to see the general picture about the phase kickback. So we are coming back to this reversible computing. So we have a Boolean function. So in the first, so that's basically what we saw in A01. And I didn't want you to calculate this this with the minus state because we will do it right now. So I won't explain it for the second time. It's the same thing we were doing previously. So now we want to substitute this y with the state minus and see actually what happens when we do that. So maybe let's copy this thing and let's follow the math that will be present. So what we are trying to calculate is UF applied to X applied to minus. We expand the minus state, so it's UF1 over square root of 2 cat 0 minus cat 1, so it's equal 1 square root over 2 UF cat X cat 0 minus UF cat X1, which is then equal to, so we'll be using this definition, like this second part. So it's 1 square root over 2. So we are leaving the first thing unchanged. So cat X is the same, but in the second we will have the Y, which is 0, XORed with f of X. And then we need to have this X remains the same. We'll have 1 XORed with f of X because we just applying 0 and 1 in the proper places. And what we can just calculate the XORs for now. So it will be cat 0 cat f of X minus cat X cat it still will be, yeah, so we can only calculate the first XOR for now. So this is the part in which we need to take a closer look at the possible values of the f of X. We know that those are only 2 possibilities. So the first one is that f of X is equal to 0. So in this case, cat of f of X, it's cat 0 and 1 XOR cat of 1 XOR f of X is 1 XOR 0. So it's 1. And when we substitute that into the formula, we will have that the state is 1 over square root of 2 cat x 0 minus cat x 1, which is equal to x. We can have 1 over square root here. And we see that this state minus, so it's cat x minus. And in the second case, the value function f of x can be equal to 1. So cat f of x is cat 1. And 1 XOR f of x is cat of 0. So what we have from that is that we have the state cat x in the first cat will be 1, in the second it will be 0 when we pull out in front of the parentheses the cat x, we will have something like not only x, but we need to remember about the minus, I think. So no, okay, we can have it like that. And so this is the minus state. So because we can have minus in here and change the signs. So it's minus x minus state. So, oh no, I wasn't showing that. I'm sorry. So basically what I did is I calculated f of x for 0 and just applied these values into the formula. So when the function is 0, the value of this black expression is x, cat x and tensor product cat minus. And when the value of the function is 1, we have the following expression. And the value of what we are looking for is minus cat x minus. So this was just like some side notes, but we can continue this black expression. So when we know that, so this black expression can now be in the form it's minus 1 to the power f of x cat x cat minus. So actually we just want to be able to express this. So we want to have like a phase factor in our formulation. So we are using this minus 1 to the power f of x, because if f of x is 0, this first case, we will have minus 1 to the power of 0, which is 1, times x, cat minus. And in the second case, when the f of x is equal to 1, this phase factor will be minus 1. And it is the same as the thing we calculated in here, that we just want to have a minus. So that's just a trick that works with a phase kickback. So when we have some transformation, it's a transformation from like a binary function with n qubits to a single qubit. And when we are like calculating it using an XOR, actually the phase is kicked back, I think, to the first qubit. The second qubit is like the same, it remains unchanged, but the sign phase changes in the top qubit. Do you have any questions to that? Okay, so now it's time we go to the Deutsch algorithm. So we don't have much time. So I will start with the presentation and we will see how many tasks can we implement. So in the Deutsch algorithms, we have Boolean functions, and the argument to this function can be either 0 or 1, and the output will be also either 0 or 1. So it's a very simple function, but it's actually not one function, it's 4 functions. So what are the possibilities? So the first one is that it's constant 0. So f of 0 is 0, f of 1 is also 0. The second possibility is constant 1. So f of 0 is 1 and f of 1 is also 1. The third option is that it's like it behaves just as an identity function. So f of 0 is 0 and f of 1 is 1. And the last option is that it behaves like negation. So f of 0 is 1 and f of 1 is 0. So we have 4 functions in total. I would call them constant 0, constant 1. Okay, I'm just getting ahead of myself, but balanced identity and balanced X. So the question now is, in how many steps can you distinguish functions in which f of 0 is equal to f of 1 from functions in which f of 0 is not equal to f of 1? I will give the answer in a second. So in the classical way, the answer is 2, because you really need to check what's the output for the first input and what's the output for the second input. So that's in the classical word, using, like, let's say pen and paper. But if we take a closer look at that, we can divide these functions into 2 groups. So in the first group are the functions for which f of 0 is the same as f of 1. So this function f0 and f1, and the functions in which the outputs are not equal. And this is an important thing. In here, half of the outputs are zeros and half of the outputs are 1. And this is on the right-hand side, this is what we called, when we call that a function is balanced, we call it when like half of the inputs is 0 and half of the outputs are 1. Sorry, I'm just checking if there are any questions. You're not able to see what's written. Yeah, so that was the thing about what I wrote earlier. Sorry, but didn't get the question. So I will just briefly say the question was, in how many but by step I mean trials of classical trials of inputs. Can you distinguish functions from which the output for both of the inputs is the same from the functions for which the output from both of the inputs is not the same? Okay, somebody replied in a very nice manner. Thank you. Yeah, so now we have things that are called constant functions and then the balanced functions. So yeah, in constant functions, the output doesn't change, and in the balanced function, half of the output is 0 and half is half are 1s. So the thing is, on a quantum computer, this can be checked in 1 step instead of 2 steps. And the purpose of using this, so it's not like a very big speed up, but tomorrow, we will see the Deutsch algorithm, in which you will see that the speed up is exponential. But here it's like this is the first step to understanding the next algorithm. So in Deutsch algorithm, we are answering the question whether the function belongs to the group constant 0, constant 1. So whether it's constant, or whether this function belongs to the group with the identity or negation and is balanced. So the Deutsch algorithm doesn't give the answer to which function exactly it is. So we won't know whether it was f0 or f1 or fx or like fi. We will just know whether this function that was that we were trying to assess, like in this one step, that it is either constant or balanced. So basically we are checking whether f of 0 is equal to f of 1 or whether f of 0 is not equal to f of 1, and we can do that in a single step. And let me see, how much time do we have? 25 minutes. Okay, because there are two things I want you to do. And the first thing is very well explained in here. So maybe we should start. Yes, so unfortunately, I think I will need to skip the part when I will calculate using the whiteboard the exact states that are in so what is the output of the algorithm after each step. But we will do something which is also helpful, and then we will come back to this circuit, to the analysis of the circuit in the next step. So for now, we will focus on the task number 1. And for that, you don't really need the analysis of this algorithm. We'll try to do that. But it will be helpful for us if you just could implement the quantum circuit that is needed in the Deutsch algorithm. So it's just creating a circuit with 2 qubits, applying X, Adamart gates, the oracle that is written. So it's written in here how to implement oracle, because oracle should be like kind of, okay, it's not like an import, but it should be taken from some other place. And then we will come back to this analysis, and then there is also an Adamart gate at the end. So yes, that's the task for now, to implement the task number 1. But watch out, there is a mistake in this notebook. In the comment here, it says apply H to the qubit number 1. No, you should apply it to the qubit 0. And measure qubit 1. No, it should be measure qubit 0. And please do that. You will have around 5 minutes, and then we will talk a little bit more about the Deutsch algorithm. I can see that people are still working, so 1 minute more. Okay, I will show the solution now. If you need more time, you can try to do it yourself later. So basically, you just need to create a quantum circuit with two qubits and 1 classical bit, because from the illustration here we see that only the top qubit is measured. So then we need to apply X to the bottom qubit and H to both the bottom and top qubits. So maybe if I put another barrier in here, it will be like easier. No. Yeah. Oh, it should be 0. So we apply X to the bottom qubit. Then we have 2 Adamant gates, CNOT and Adamant, and we are measuring the top qubit. We will analyze, if not today, probably not today, we will analyze the in-depth how it works, but tomorrow will be the day of the Deutsche algorithm and we will be able to do that. So as for now, it's just related to how to prepare the circuit. And we will also do the task number 2, because it will show us something very nice, and then it will be easier to understand how this algorithm works. So this is the quantum circuit you've just implemented. So it's X, H, H, oracle, H, and measurement of the top qubit. So let's, and oh, sorry, I didn't say what the task 2 is. So there are 4 possible functions, f of x, and we already identified them because I told you what they are. So there are 4 options: constant 0, constant 1, kind of like identity and negation. And we need to implement the oracle functions that implement each of these 4 functions. So we will need to write 4 oracles, because in here we are just like taking some external oracles, and this oracle is between these 2 barriers. So in here we have like some kind of an oracle, another oracle, another oracle. So we actually saw all the 4 different versions of oracles. We got lucky. And in here we need to implement them on our own without using this this external implementation. So let's try to see how to do that. So this is the task number 2. We will try to do it together, at least for the first version. So we know that the oracle, so that's the oracle we've seen many times today. We have data qubit, target qubit, and then the data qubit remains unchanged, and target qubit is just applying this y to the function it actually represents. I think that's the thing about oracles is not written in here, but that's basically the same oracle we've seen all of the time today. So let's try to elaborate on that a little bit. So assume that we are now calculating the, so what are the functions? So that I said that there are 4 functions, and the functions are f0. So it's constant 0. The next function is constant 1. The next function is identity. So it's a balanced function. It's 0, 1. And a negation, which is 1, 0. I hope you can see that. You can. Okay, so now we will calculate for all of these 4 functions how the oracle behaves. So let's start with this first, f0. So we will implement that. So how do we do it? So we are taking, so we need to take a look at how the oracle works, and then basically write the same things in the proper places. So let's start with the case where the input is all zeros. So in the top qubit, we are just writing the same thing that was in the input, and in the bottom qubit, we are actually writing that it's so now we are calculating UF of 0. Okay, and in the bottom qubit, we need to calculate the value f of x, which is, the x is 0, so f of 0 is 0, XOR the value of the bottom qubit, which is 0. So XOR 0, 0, it's 0. So this is the behavior of the oracle constant 0 for the function f0, for the input 0, 0. So we need to check this behavior of this same function for the input 0, 1. So the top qubit remains unchanged because the data qubit stays the same. And on the bottom we have 1. So we'll have the value. So the first thing in XOR is f of x. So f of 0, because 0 is the input, is 0 XORed with 1, and this is actually 1. Then we have the third oracle. So the input qubit remains the same, and in here we are taking the f0 of x, so x is 1, so f0 of 1 is still 0 because it's constant 0, XOR y, which is 0 because that's y, and we have 0 in here, so it's 0 XOR 0, which is 0. And in the last case, the input qubit remains the same, and the target qubit, so we are calculating, so this is f0, because I should have probably written that, f0 of the data qubit, so it's f0 of 1 XOR the value that is on the bottom qubit, which is 1. So what we have here is 0 XOR 1, which is 1. And what we see in here is that this f0 oracle behaves in a way that basically does not change anything. So if the input was 0, 0, the output is 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1. So the oracle for the constant 0 doesn't have any gates. So if we have the constant 0, we just leave empty wires. Now, so that is the thing you need to implement in this. So you have like 3 places in which you can implement this oracle. You can say that it's oracle 1. So in fact, it can be implemented already because you don't need to change anything. So maybe let's see. Yeah, we will manage to do 2 more oracles. So let's do it. Okay, so maybe I will do 1 more oracle, and then there will be time for questions. And so we already did. The constant oracle. So let's do a balanced oracle, and we will do the x case. So now we will try to implement this fx oracle. So here was f0, and here is not f1, it's fx. I will erase everything. So yeah, we can write it. So the top qubit is always unchanged. I will write that. Yeah, you could probably see that. Yeah, so the top qubit remains unchanged, and the bottom qubit is the value, it's cat fx of the input, which is 0, XOR the target qubit value. So is 0. So fx of 0 is 1. 1 XOR 0 is 1. In the second case, top qubit stays the same. On the top, we have fx of 1, which is 0 XORed. No, we have fx of 0 because 0 is on the data qubit, XOR, and this is 1. XORed with 1, which is on the bottom qubit. So 1 XOR 1 is 0. In the third version, data qubit stays the same. In here we have fx of data. Data is 1 XORed with the value that is on the bottom qubit. So this is 0. Fx of 1 is 0. 0 XOR 0 is 0. So we leave 0 in here. And in the third case, we leave 1 remain the way it was. And in here, it's fx of 1, which is 0 XORed with 1. So 0 XOR 1 is 1. So now, when we have all that, we can see how it behaves. So when we have input 0, 0, the output is 0, 1. When we have input 0, 1, the output is 0, 0, 1, 0, 1, 0, 1, 1, 1, 1. So for when the first qubit is 1, nothing changes. But if the first qubit is 0, the bottom qubit is inversed. So this oracle can be implemented in the following way. So we have 2 qubits. There is negation on the bottom qubit and CNOT after that. So in the case of 0, 0, this won't fire, but we will have 1 here, so it's 0, 1. In the case of 0, 1, this won't fire, so this will be 0, so it will be 0, 0. In the case of 1, 1, which is the last case, this will be 0 and this will fire, so this will be 1, 1. And in the case of 1, 0, because we haven't analyzed that yet, so 0 X gate is 1, and this CNOT will fire, so I'll change this 1 to 0, so it's 1, 0, which is correct. So we've already prepared the implementation for 2 oracles, the constant 0 oracle, the balanced oracle for the negation, and you always also have the implemented oracle for the constant 1. So what you need to do yourself is to implement the oracle for the balanced identity function, and I'm sure you will be able to do that by yourself for sure. It's almost 7 p.m. There are a few seconds left, so I don't want to make this this workshop too long. So do you have any questions? I will take a look at the chat. So there are actually different oracles for different functions, but the oracles are, so there's, sorry, the question is, I guess the oracle is the same, but we explain different possibilities, right? So there are 4 versions of oracles, but we don't know which one we have. So it's like not a transparent box. And we need to be able, regardless of what's inside this oracle, to guess, not to guess, to predict whether this function is constant or balanced. And if you want to have, if you want to get a better grasp of how this algorithm works, you can read this analysis. I think we'll come back to that tomorrow. But yeah, I think that will cover what we wanted to cover. I wanted to cover with you today. So that's all from my side. If there aren't any other questions, I think there will be some tasks regarding the Deutsch. There is a quiz for you. I'm not sure when it will start, but you will be notified. And in the quiz, you have some questions about the Deutsch algorithm and phase kickback, but I think we've covered everything, so that you will be able to like fill in this quiz. Okay, so if there aren't any questions, thank you for being in here with me today, and I hope to see you tomorrow.
Thank you, Justina. Thank you, Maria.
Thanks, Justina.
Yeah, goodbye.
Goodbye.
Bye.
Thank you. See you tomorrow.
See you
Thank you very
tomorrow.
much. Goodbye.
Oh no, stop recording.